morning, good afternoon or good evening, depending on your geographic location, and a very warm welcome to this LabMate Chromatography Today e-learning session on ion chromatography, with topics titled Coupling Ion Chromatography to Mass Spectrometry and Automatic Calibration in Ion Chromatography, Save Time, Gain Reliability. My name is Trevor Hopkins. I'm the editor of Chromatography Today and Separation Science and Spectroscopy editor for International LabMate Limited, and I'll be the moderator for today's e-learning session. Mass spectrometry is a preferred detection method for separation science due to its exceptional sensitivity, its ability to resolve co-eluting compounds, and the additional information it provides to the analyst for the identification of compounds. The coupling of ion chromatography to mass spec has never really been popular due to the high salt concentrations used in the elution of compounds from the ion chromatography column. In this session, we learn the historical background of ICMS, how to achieve effluent ion suppression, and the various modes of ICMS available today with accompanying applications for each mode, and then learn of current application areas and the advantages of coupling ICMS. Dr. Elizabeth Gilchrist is a researcher in the Department of Chemistry at University College Cork in Ireland, having recently obtained her PhD within the Analytical and Environmental Division at King's College London. Her research to date has focused on the development of capillary ion chromatography and ion chromatography high-resolution mass spectrometry technologies for trace analysis, publishing several papers in this area. Some house rules. Questions will be put to the presenters at the Q&A session at the end of the presentation. We will be happy to accept your questions throughout the session and encourage you to ask questions via the red Q&A box on your display. If your question is not answered for any reason during the session, we will respond via email after the session has concluded. This e-learning session will be available on demand in 24 hours, so you can re-watch the presentations and ask additional questions via the Q&A box. Should you be experiencing any problems with visual or audio, please again use the question box where our team are on hand to assist, or simply restart your browser. So without further ado, I'm delighted to introduce our first presenter, Dr. Liz Gilchrist.
Thanks, Trevor. Today I'm talking about coupling two analytical techniques
Morning, good afternoon or good evening, depending on your geographic location, and a very warm welcome to this LabMate Chromatography Today learning session on ion chromatography, with topics titled Coupling Ion Chromatography to Mass Spectrometry and Automatic Calibration in Ion Chromatography, Save Time, Gain Reliability. My name is Trevor Hopkins. I'm the editor of Chromatography Today and Separation Science and Spectroscopy editor for International LabMate Limited, and I'll be the moderator for today's e-learning session. Mass spectrometry is a preferred detection method for separation science due to its exceptional sensitivity, its ability to resolve co-eluting compounds, and the additional information it provides to the analyst for the identification of compounds. The coupling of ion chromatography to mass spec has never really been popular due to the high salt concentrations used in the elution of compounds from the ion chromatography column. In this session, we learn the historical background of ICMS, how to achieve effluent ion suppression, and the various modes of ICMS available today with accompanying applications for each mode, and then learn of current application areas and the advantages of coupling ICMS. Dr. Elizabeth Gilchrist is a researcher in the Department of Chemistry at University College Cork in Ireland, having recently obtained her PhD within the Analytical and Environmental Division at King's College London. Her research to date has focused on the development of capillary ion chromatography and ion chromatography high-resolution mass spectrometry technologies for trace analysis, publishing several papers in this area. Some house rules. Questions will be put to the presenters at the Q&A session at the end of the presentation. We will be happy to accept your questions throughout the session and encourage you to ask questions via the red Q&A box on your display. If your question is not answered for any reason during the session, we will respond via email after the session has concluded. This e-learning session will be available on demand in 24 hours, so you can re-watch the presentations and ask additional questions via the Q&A box. Should you be experiencing any problems with visual or audio, please again use the question box where our team are on hand to assist, or simply restart your browser. So without further ado, I'm delighted to introduce our first presenter, Dr. Liz Gilchrist.
Thanks, Trevor. Today I'm talking about coupling two analytical techniques, ion chromatography and mass spectrometry. There are several different ways that this can be achieved, and these should be covered along with potential applications during this webinar. I'm going to start by giving a brief background into the two techniques, ion chromatography and mass spectrometry. I'll also briefly explain the importance of eluent suppression for those that are unfamiliar with IC. I will then discuss the different modes of ICMS, including ion interaction, chelation IC, IC coupled to inductively coupled plasma MS, and finally ion exchange. Throughout the presentation, I'll include several applications to provide examples of these modes and to highlight the potential ICMS has in a number of fields. ICMS has been growing in interest in the last few years. Although not the most accurate search, this slide shows that hyphenation of IC to MS is not a new concept. And with the recent advances in the technological side of both IC and MS, coupling the two techniques together is increasing in a wide range of scientific fields, from pharmaceutical to forensic to environmental. For those familiar with IC, it is a form of liquid chromatography which separates analytes on the basis of charge and size, mainly inorganic ions, low molecular weight organic ions, and organometallic compounds. There are several modes of IC, including ion exchange, ion interaction, and ion exclusion chromatography, some of which will be discussed today. Currently, the most common form of detection used in IC is conductivity detection due to the charge on the analytes, although UV, pulse damperometry, and obviously MS are also used. However, with the exception of MS, these detection modes are unspecific, relying on matching retention time with standards to offer a possible identification. MS produces spectra of the masses of the molecules in the sample, enabling you to gather elemental information and elucidate their structure, making it much more specific than other detectors. There are several types of mass spectrometer. The most commonly utilized of IC are quadrupoles, which can be single or triple, or alternatively ion traps, which can offer higher resolution. There are several interfaces employed to couple IC to mass spec. The majority of the methods covered today use electrospray ionization, shown here. This mode of ionization is a soft ionization technique, as the energy transferred is often too small to allow fragmentation to occur, meaning a pseudo-molecular ion is observed. Alternatively, atmospheric pressure chemical ionization, or APCI, can be used. It differs to ESI in that the solvent evaporation and analyte ionization occur in two stages. APCI tends to give better sensitivity for less polar compounds and is less sensitive to sample matrix and eluent composition effects than ESI. Inductively coupled plasma is an alternative ionization technique frequently used when coupling IC to MS for the analysis of haloacetic acids and metals. This is discussed in more detail later. The low mass cutoff can range from about 20 to 50 units depending on the mass spec instrument. An IC will analyze low molecular weight compounds, for example fluoride with a mass of 19, so it may be necessary to still utilize a secondary detection source, such as conductivity. Suppressors are arguably one of the most important devices in IC. They lower background noise by removing the highly conductive eluent ions, such as hydroxide, and replacing them to create water. Nowadays, suppressors are either membrane-based or packed bed, which are capable of being continuously regenerated, such as the MSM produced by Metrohm. Not only is this important for improving sensitivity for conductivity detection, but it also prevents damage to the mass spec. There are two main types of membrane suppressor, chemical and electrolytic. Electrolytic suppression uses a current to electrolyze water and generate hydronium ions, which passes through the membrane into the eluent chamber to form water with hydroxide, which lowers the conductivity. Once the water in the eluent has exited the detector, it is then rerouted back to the regeneration chambers to help suppress the incoming hydroxide eluent. It is not always possible to use the eluent as a regenerant, such as when it is modified post-column or coupled to mass spec, and therefore an independent source of water can be used in external water mode. Typically, though, these suppressors can only be used with up to 40% organic solvent. Chemical suppression uses a manually prepared strong acid regenerant to generate hydronium ions instead of a current, and although it requires the use of a secondary pump, they are compatible with higher concentrations of organic solvent. Metrohm instruments are fitted with packed bed suppressors regenerated by a tri-chamber sample exchange rinse rotation. Only one column is used analytically at one time, whilst the others are either being automatically regenerated or washed online before being sequentially rotated into active eluent suppression. Like the chemical membrane suppressors, sulfuric acid is normally used as a regenerant when in the exchange position. An advantage of this suppressor is it's compatible with 100% organic solvent and tolerant to much higher back pressures than membrane-based devices. So on to modes of coupling. The four I'll be discussing are ion interaction chromatography mass spectrometry, chelation-based ICMS, IC coupled to inductively coupled plasma MS, and finally suppressed and non-suppressed ion exchange chromatography mass spectrometry. Ion interaction chromatography is typically performed with silica C18 or C8 groups with ion pair or ion interaction reagents. These IIRs are required to be lipophilic to bind to the stationary phase, but also hold a charge to affect retention. There are several ways this can be achieved. You can permanently coat the stationary phase using a preliminary step, where the IIR binds to the reverse phase column as a semi-stable layer. This facilitates the use of universal detection modes, but can suffer surfactant bleed. You can also dynamically coat the column, where the IIR is present as a constant concentration in the eluent. The partition model, the analyte when injected, interacts with the IIR in the eluent first, and can partition into the stationary phase and get retained. With the absorption model, the IIR present in the eluent gets absorbed into the non-polar stationary phase first, forming a pseudo-ion exchange layer on the surface to then retain the analyte. It is important to pick an IIR compatible with the detection mode. For example, it is not possible to use tetraalkylammonium salts as the IIR with mass spec because they contaminate the interface and can form cluster ions with anions, which reduces the sensitivity. This slide shows the use of ion interaction chromatography to detect haloacetic acids in water. Research by Takina used ICMS to separate a series of 9 haloacetic acids using dibutylamine as an IIR and a shallow gradient of acetonitrile. Acceptable separation and peak capacity was achieved under these conditions, but the method required a post-column supplementary proton 2R flow prior to the ESI source to boost mass spec sensitivity to direct nanogram per litre determinations using large 500 microliter injection volumes. However, due to the need for low flow rates for ESI, the analysis time is increased when compared to conductivity. Luz et al. Also investigated IICMS for the separation of 9 haloacetic acids. The authors used triethylamine as an IIR in a gradient of 15 to 50% acetonitrile instead, and did not require a supplementary flow of organic solvent. This mode of IC uses surface-grafted ligands, such as aminodiacetic acid, on a stationary phase support, and has been applied mainly to the separation of metal ions. Chelation-based IC may also be performed by adding chelating ligands to the eluent to disrupt complex formation at the stationary phase, or electrostatic interactions when using an ion exchange resin to effect solution. The advantage of chelation IC is often observed in its ability to determine ionic species in highly saline samples, such as seawater. However, due to the requirement for high ionic salt concentrations in the eluent to suppress exchange, there is the possibility of contamination of ESI sources or analyte ion suppression. However, this approach has been demonstrated using both ESIMS and ICP-MS. Collins et al. Demonstrated the pretreatment of samples with ethylene diamine tetraacetic acid, EDTA, to effect a 12-minute separation of metal EDTA complexes having a net negative charge, with an isocratic eluent of 2.5 millimolar ammonium carbonate, 9.7 millimolar ammonium hydroxide, and 4% methanol. Sensitive mass spec detection was facilitated using an auto-regenerated electrodialytic suppressor, and ESI was operated in negative ionization mode. Detection was performed mainly by selected ion monitoring of the precursor ion N-H where possible. Although it was possible to detect N-2H given an overall 2- charge, as well as corresponding fragment ions via losses of 1 or 2 carboxylic functional groups from the EDTA molecule. Given the structure of EDTA, positive mode ESIMS was also possible, though negative ionization mode offered better detection limits in the low sub-micromolar range for manganese, zinc, aluminium, cadmium, and copper EDTA complexes. This shows the separation of a 50 micromolar standard, and the authors then went on to study soil solution and xylem exudate samples. Hard ionization technique, ICP, is an alternative to atmospheric pressure-based techniques and is particularly useful for elemental analysis. In particular, ion exchange ICP-MS has been used more widely for the detection of metals and selected non-metal species. The ionization process involves the nebulization of an IC eluate and passage through a high-temperature plasma, where desolvation and atomization occurs, generating analyte ions. The partial ionization of argon gas via application of a current to an electric coil is the most common means to generate the plasma. However, it can be very sensitive to isotopic interference produced by polyatomic species arising from the plasma. Work published on trace ion exchange ICP-MS involves the use of low carbon containing eluents, and the use of carbon-bicarbonate eluents without suppression has been shown to decrease sensitivity in ICP-MS through contamination of skimmer scones. On the other hand, the use of eluents such as nitric acid, ammonium nitrate, or ammonium hydrogen phosphate generally have not required a suppressor and could be coupled directly whilst maintaining sensitivity at the nanogram to picogram level. A multi-analyte ICP-MS method was demonstrated by Pantar-Kallio et al. Using a gradient of nitric acid, potassium nitrate for the separation and detection of 8 halogenides and oxyhalogens in drinking water. Using the Waters IC Pack A, which is a standard board trialkylammonium functionalized polymethacrylate resin, the authors developed a fast separation in under 7 minutes. Nitric acid did not introduce any significant interference or result in cone contamination. The detection of chromium and arsenic-containing compounds such as chromium, chromate, arsenate, and arsenite also frequently utilizes ICP-MS. Both chromium and arsenic species are known to suffer isotopic interference from carbon and chlorine-based species in ICP-MS. Regarding the formation of the interference species, the use of organic solvents is therefore not recommended for chromium or arsenic analysis. The inclusion of collision cells into ICP-MS instrumentation for tandem MS has greatly reduced the interference effect by dissociation or fragmentation of interference and results in improved specificity for analyte elemental analysis. Ion exchange chromatography is arguably the most utilized mode of IC, particularly when coupled to mass spec. There are several ways this can be achieved. Addition of solvent post-column or suppressor to assist in volatilizing the eluate, post-column or suppressor addition of an ionic reagent to form ion association complexes, or direct coupling, which can involve adding organic solvent pre-separation. The majority of IC separations operate under aqueous conditions. For coupling to ESI sources, IC eluates are often modified post-suppressor with organic solvent to improve sensitivity, but it does require a T-piece and tertiary pump to feed the solvent in. This is common as membrane suppressors are typically only compatible with up to 40% organic solvent. However, this method can lead to added back pressure which could potentially damage suppressors, particularly membrane-based. It is also important to consider band spreading and dilution of the analytes, as well as the possibility of incomplete mixing, which may affect your sensitivity. Barron and Paul determined a range of analytes, including inorganic anions, oxyhalides, and haloacetic acids in soils and water matrices. This method used a hydroxide gradient with supplementary flow of methanol post-suppressor in order to volatilize the eluate for ESI. As I mentioned, sensitivity can be affected. However, in this case, LEDs were reported between 2 to 138 micrograms per litre using a linear ion trap. Post-suppressor addition of an ionic reagent is set up in an identical way, except there will be an ion interaction reagent present in the organic solvent. The use of ion association complexes in mass spectrometry of low molecular weight inorganic ions have been documented over the past 15 years or so as a means to enhance selectivity, sensitivity, and in some cases signal stability. For ion exchange MS of anions, ESI has generally been used in negative ion mode. The use of ion association complexes with dicationic reagents has been demonstrated for anion detection in positive ESI mode. There are advantages to operating in positive instead of negative ESI mode, such as a decreased risk of corona discharge and arcing. The use of ion association complexes can also potentially improve sensitive quantitative determinations of these types of species, offering increased signal intensity due to more efficient electrospray, as well as improved selectivity due to a higher mass to charge offset as an association complex, reducing background interference and noise. Sukup Hein et al. Showed that a dication anion adduct in the positive mode gave significantly better signal to noise and higher area counts in the negative mode for 4 out of the 5 anions detected in a tap water sample. An alternative method is to include organic solvent for ESI in the eluent pre-separation. This allows you to cut out the tertiary pump and T-piece. However, the presence of organic solvents in the eluent may cause some changes in packing bed volume, which may lead to effects on retention, separation selectivity, and efficiency of the analytes, as well as system back pressure. To be compatible with ESI, lower flow rates are generally required, whereas too low a flow rate for the separation increases band broadening. Typically, researchers have employed microbore analytical columns at flow rates between 0.1 to 0.7 mils per minute, which arguably may perform better than using capillary scale technologies, which may be too low for coupling to typical ESI MS and too high for 9 spray ionization. As I've mentioned several times when discussing the different modes, it is also important to consider your eluent compatibility, not only with regards to the chromatographic resin and suppressors, but also with the mass spec and ionization source. It is also important to consider the ionization of your analyte in the eluent. For example, sulfate in a neutral eluent, such as post-suppression water, will be singly charged, not doubly, which can affect the mass you're looking for. Finally, sources of post-suppressor back pressure also need to be characterized carefully. The ionization source, flow diverter valves if used, as well as any supplementary solvent introduction, generate back pressures. High back pressures can be irreversibly damaging, and therefore it is important to keep within instrumental limits. The effect of organic eluent modification on the signal intensity of small anions has been studied using a range of concentrations of acetonitrile and methanol in ultra-pure water. A significant gain in intensity can be seen with a small modification of 20% acetonitrile. And for water methanol-based solvents, signal intensity increased steadily up to 60% and subsequently decreased. This shows that overall there is no obvious advantage in using high percentages of organic solvent, and similar maximum intensities were observed for both solvent additives. Relatively lower solvent compositions could be considered advantageous for practical coupling to mass spec for small anions for several reasons, including increased solubility of sodium hydroxide in the eluent, improved suppressor performance and potential operational lifetime, and increased mass spec sensitivity through improved electrospray generation. Perchlorate is particularly toxic to humans at low concentrations through preventative uptake of iodine, resulting in hypothyroid function, and is therefore monitored globally. One of the two chromatographic methods specified in the US EPA Method 332 for the specific detection of perchlorate in drinking water uses a standard bore Metrohm A sub 5 with an eluent of 30 millimolar hydroxide and 30% methanol. This method used a pat spread suppressor to ensure compatibility with the organic solvent in the eluent. It was possible to achieve detection limits for perchlorate in water at 0.02 micrograms per litre using large 200 microliter injection volumes and a quadrupole mass analyzer. However, as organic solvent in the eluent pre-separation can lead to unpredictable retention behaviour, for identification, naturally occurring perchlorate present in the samples was measured relative to an 18 oxygen enriched perchlorate internal standard to ensure reliable retention time reproducibility. The addition of solvent can greatly affect the retention, as well as the elution order of the analytes. Although not shown on the selectivity plot, as perchlorate is fully retained on all the resins shown in aqueous conditions, with the addition of 35% acetonitrile, it is shown to elute within 30 minutes. With the further addition of 60% acetonitrile, perchlorate actually elutes before thiocyanate and phthalate on the AS18 resin, with an almost complete reversal in selectivity. Runtimes can be greatly reduced with even a small amount of organic solvent added into the eluent. It is very important to check your resin is compatible with organic solvent though. Mass resolution is the ability to distinguish between two adjacent peaks in the mass spectrum. Quadrupole analyzers are low-resolution mass analyzers and can generally distinguish reliably between a single mass unit. However, molecules with different elemental compositions can have an identical nominal mass, requiring greater resolution or fragmentation patterns to confidently distinguish between them. Mass accuracy measures how close the measured mass is to the true mass of the analyte. High-resolution, accurate mass instruments are a fairly recent advancement in mass spec and are very useful when analyzing small ions, such as those frequently targeted in IC, which may suffer increased interference, where utilizing fragment patterns for a more confident identification is not always possible. An example of the resolving power of HRMS is shown here. Intense background signals using a lower resolution instrument showed the presence of the bisulfite ion at mass 97 with an isotope at 99. Perchlorate, as mentioned earlier, is an important analyte in environmental and forensic analysis and also has a mass at 99, which reduces the confidence in its identification. Using HRMS, two bisulfate isotopes measuring 98.9555 and 98.9640, which shared a nominal mass of perchlorate, are easily distinguished from perchlorate at mass 98.9491. Recent work coupling IC to HRMS was demonstrated by Burgess et al. In the field of metabolomics using capillary scale 0.4 millimolar ID columns and suppressors, resulting in femtomole to picomole sensitivity for biomolecules. A supplementary makeup flow of organic solvent was used to aid eluent volatilization. 34 organic acids and sugar di- and triphosphates ranging between 80 to 500 mass to charge were analysed with a resolution setting of 50,000 full width at half maximum. Positive identification was on the basis of retention time and a mass accuracy within 3 ppm. This slide shows the separation achieved for 11 forensically relevant ions using solvent-enhanced chromatography coupled to high-resolution mass spec. This utilised 35% acetonitrile in the eluent, allowing the perchlorate to elute within 30 minutes on this particular resin. This method led to the detection of a black powder substitute, pyridex, in latent human fingerprints deposited on glass substrates. Benzoate, nitrate and perchlorate were all detected in agreement with previous work using suppressed conductivity detection. However, using the more sensitive IC-HRMS method, it was also possible to observe clear signals for chlorate and phthalate at trace concentrations. All species were detected with ion intensities above 10 to the 7, which was considered acceptable for negative mode electrospray ionization. One of the advantages of mass spec, and in particular high-resolution mass spec, is the ability to detect isotopes, which can assist in analyte identification. This slide shows 2 intense ions for chlorine-35 and 37 contributions for perchlorate in contaminated finger mark extracts in an approximate 3:1 ratio as expected with chlorine isotopes. The advantage to using mass spec detection opposed to conductivity is the increase in sensitivity, with absolute sensitivities improving between 7 to 163-fold when using MS detection for this particular method. Absolute LOQs using solvent-enhanced IC-HRMS range between 8.2 picograms to 4.9 nanograms, calculated using a signal-to-noise ratio of 10 to the 1, and a lowest concentration range peak error variance limit of less than 20% RSD. Whilst this was a rather conservative definition of LOQ, it was comparable to the other published IC-MS methods shown here. The advantage I will mention is in trace detection in a complex matrix. This slide uses chlorate in a mixture as an example to emphasize the attraction in employing selected ion monitoring over non-specific options such as conductivity in order to limit interferences and avoid false positives. ICMS technologies make a strong contribution to the analysis of a range of application types such as environmental and forensics. ICMS offers advantages over other analytical techniques in terms of its ability to speciate, which is essential in the identification of analytes such as oxyhalides, as well as offering selectivity and sensitivity over traditional non-specific detection modes such as conductivity and UV-Vis. Well-established ICMS methods out there, there is still opportunity to develop the use of ICMS further. Some potential areas are in improving the coupling of capillary IC to mass spec, using HRMS for semi-targeted screening, further development of ion association reagents, as well as dual analysis for more informative and efficient analysis. There is more information on this topic available in a review that was published last year for those that are interested. And finally, thank everyone involved with the work in ICMS, as well as those helping who put the presentation together, and also those that provide funding and support. And lastly, I'd like to thank Trevor and Rob for organising today's event and everyone for listening.
Genau. Und wie siehst du das halt passt schon ziemlich gut? Genau so habe ich mir vorgestellt. Genau so. Und schwächer mit der Verbindung.
Ja, schon runter aus.
Ja, super.
Thanks to Metrohm, ion chromatography has become a standard analytical technique. Simple to use, robust and reliable. Many things that used to be complicated are now quick and easy. Sample preparation is fully automated and integrated into your Metrohm IC system. This saves time and ensures that results are accurate and reproducible. Metrohm IC is very economical. The suppressor for an ion chromatography comes with a 10-year guarantee. Why not arrange for a demonstration? We'll gladly show you how you too can save time and money with Metrohm IC.
Zuerst verdünnen und dann mit der Filtration filtrieren und dann injizieren.
Thank you, Liz, for that very interesting and informative presentation. Our next presentation is by Dr. Andrea Villet, who is the manager of the Ion Chromatography Competence Centre of Metrohm International, headquartered in Herisau, Switzerland. She's worked with ion chromatography for 20 years, 15 of those years at Metrohm. In this time, Andrea worked as an application specialist as well as a product manager for ion chromatography. Since 2007, she's been responsible for the sales and marketing of Metrohm's ion chromatography instruments. This session explains the technique of ion chromatography and shows the capabilities of the new ion chromatography automatic calibration methods that are available and have been engineered to save time and improve the precision and reliability of results that in the past were done manually. Additionally, tips and tricks for ion chromatography calibrations are given to aid all ion chromatography applications. I'd like to now ask Andrea to present her presentation. Thank you.
The introduction and a very warm welcome also from my side to this presentation, Automatic Calibration in Ion Chromatography. I will show you today different techniques how you can do this automatic calibration, as well as a technique how you can enlarge the calibration range by high-low calibration. The last part of the presentation are tips and tricks for calibration in ion chromatography itself. The calibration in ion chromatography. IC is a relative analysis method. It means we need a calibration to quantify unknown samples. This calibration describes the relationship of concentration and measured signal which can be obtained using standards of known concentrations. And by this calibration curve, you can measure your samples. Usually you use a multi-point calibration in ion chromatography to increase the accuracy of the results, because only if the results are within the calibration range, they are reliable. The calibration standards are usually prepared from a concentrated multi-ion standard by manual dilution. But that is a time-consuming and error-prone working step, and therefore an automation of this step would save time and gains reliability. Therefore, automatic calibration. That means that you have to prepare only one single multi-ion standard for your whole calibration, for your whole multi-point calibration. The benefits out of that are clear. You have more convenience in the handling, you reduce the preparation time, less error-prone manual working steps, easier validation because we reduce the operation influence, as well as an improvement for the precision and the reliability of the results. For automatic calibration, we know different techniques which we can use. Starting with inline dilution techniques that I will show today, as well as the Metrohm Intelligent Metrohm intelligent loop technique, two techniques which are usually used in the environmental field. These two I will show today. Besides that, there's also the pick-up injection technique possible for automatic calibration. It is used if only a very small amount of sample is available. Pre-concentration techniques with or without inline matrix elimination are also possible to use for automatic calibration. Two techniques which are used for nanogram per liter as well as microgram per liter concentration range, and inline calibration, a technique if you have to work with nanogram per liter range. The Metrohm inline dilution technique. The first technique which I would like to explain is the Metrohm inline dilution technique. You see here on the slide how it is running. On the right side you see the ion chromatography system, on the left side the liquid handling part. And the needle is already in the sample and aspirates the sample to a buffer tubing. The buffer tubing is about 10 milliliters, so you have enough space for your sample. Now the needle goes to the liquid handling station, here to the dilution vessel, and enters this sample, as well as an air gap, which is a separator between the sample and the dilution medium, which is now entered to the liquid handling station. Dilution medium can be ultra pure water or also another medium. Now it is stirred, and then the diluted sample will be transferred by an external pump to the injection valve. The injection valve is in fill position, the loop is directly rinsed with the diluted sample, and after a certain while it goes to inject. Usually you say 3 times the injection loop should be rinsed. Quite often it is more. After injecting, then the diluted sample will be entered to the column, and there the different ions will be separated and later on detected in the conductivity detector. The inline dilution technique is an automatically sample preparation technique which is done during the sample delivery. You can use it for samples as well as for standards with an unlimited dilution factor. 1 to 2000 is the maximum for a single dilution, but you could use also a multiple dilution, and so unlimited dilution factors here. The technique can be used for anions, for cations, for sugar analysis in different matrices, quite often with a high ionic matrix. Parallel independent systems for anion and cation analysis parallel are possible. The usual concentration range for this technique is milligram per liter to gram per liter range. And it is quite often combined with inline ultrafiltration, because most of the samples in ion chromatography has to be filtered before you enter this in your system to protect the system, to protect the separation column. And here an automatic combination of both techniques helps you to save your system. Inline dialysis can be also used. So a technique which saves time and cost and is used quite often for routine applications or wastewater applications, as well as in the food and pharma industry. We use this technique now for automatic calibration. Because of the excellent linearity of this technique, it is only necessary to prepare one multi-ion standard. And by different dilutions, automatic dilutions of this single standard, you get a multi-point calibration curve. Let's see here an example. The standard solution 50 milligram per liter. If you dilute it 1 to 2, you have 25 gram per liter and 1 calibration point. If you dilute 1 to 5, you have 10 milligram per and the second calibration point. If you dilute 1 to 10, you get 5 milligram and the third calibration point. If you dilute further on, it's 1 to 20, 2.5 milligram per liter, and 1 to 50, and this 1 milligram per liter. And you see, you get automatically a curve. And this not only for one ion, it can be also for multiple ions. if your stock solution has different ions included. So different concentration ranges for different analytes are possible. A technique where you can expect really good correlation coefficient. Here you see the example for cations with more than 4 nines, as well as a precision in this example with less than 0.5%. Another example I'd like to show you here, anion analysis. We see also different automatic calibrations, the correlation coefficients higher than 4 nines, as well as also the relative standard deviations in the range of 1% for all of these anions. If you see an example for cations, and here a dilution of 1 to 1000 in one step, then we have here a calibration curve shown for sodium, and also here the relative standard deviation is less than 1%. You see the statistics of all the different cations which has been calibrated here parallel in the upper table, with the correlation coefficients higher than 4 nines for the most of the cases, and also the relative standard deviations are excellent. You can verify such a calibration curve by check standards. And that is done here, and the recoveries of this check standard are in a range between 98 and 100%. So really good, and also the precision of this check standards less than 0.7% in this case. We can use the inline dilution techniques also for samples. And that has a big advantage. We can enlarge the calibration range by that. You see here your calibration range in the slide, and if you measure then a sample, the peak areas are compared with the standard peak areas. And if they are within the calibration range, everything is fine and your final results are reported. If they are out of the calibration range, the sample is automatically diluted by the optimal dilution factor, and this optimal dilution factor is calculated by the system itself and then automatically re-injected. So at the end of the day, you have all the samples within the calibration range, and that helps you a lot that your results are reliable for all the sample series. That is also shown here. Logical dilution always use the optimal dilution factor that is calculated automatically. Only a single method is necessary for this technique, so the maintenance of the method is really less, as well as nearly no maintenance is necessary, and you can run high concentrated and low concentrated samples directly behind each other. So the results are always within the calibration range, and that, of course, increases the accuracy and the reliability of your results independent from the initial concentration. The complete sample concentration range for this technique can be 1 to 4 million. So we have here really a huge range which you can cover with a single automated calibration. The second technique which you can use for automatic calibration is the intelligent partial loop injection technique. Here you see again how it works. The first step is the pre-rinsing step of the whole liquid handling side. Now the sample needle goes to the sample position and transfers the sample to a buffer tubing. The buffer tubing in this case is about 2 milliliter, so smaller than inline dilution. Now the needle goes again to the liquid handling station, but here to the waste position. You see now the injection valve is going to the fill position, and the 800 decino does exactly this volume which you would like to inject in your system to the sample loop. And after injecting, this amount of sample is transferred to the column and later on to the detector that you can measure. The application range for this intelligent partial loop injection technique, it's also clear you can use it for samples as well as for standards. It has a high flexibility because the volume can be variated between 2 and 200 microliter. You can use it for amines, for cations, for sugar analysis, double-channel systems. The typical concentration range for this technique is lower than inline dilution. Here we speak about microgram per liter, milligram per liter range. And it can be also combined with inline ultrafiltration. So a universal application for trace analysis as well as for wastewater analysis in the same run, in the same sample series. So huge concentration differences are possible, used quite often in, let's say, contract labs or labs which has a huge sample or numbers of samples to be handled. We can do an automatic calibration with this technique. Also here we have a huge linear range, and therefore you have also only to prepare one multi-ion standard as a stock solution. Let's see here an example with 100 microgram per liter stock solution, and then you use different injection volumes of this stock solution. And by that you get also different concentrations in your calibration curve. You can use it again for different analytes in the same calibration set, as well as the concentration ranges can be different. A few examples here for cations. You see standard cations including ammonium as well as zinc. Also here you see the correlation coefficients are excellent, more than 4 nines, and also the relative standard deviations are in the range of 1%, calcium here 2%. It's also fine. We can use MIPT technique also for measuring samples, and here we do the same. We compare the peak areas of the sample with the highest standard. If it is within the calibration range, everything is fine, the results are reliable, and the results are reported. If it is out of the calibration range, the system automatically calculates the optimal injection volume, which would be necessary for this sample. And this injection volume can be also vary in between 2 and 200 microliter. So you have again a factor of 100 for the sample. In the calibration range, also a factor of 100. That means together you can cover with one calibration here a concentration range of 1 to 10,000 with this technique. And that's quite nice, as well as much faster and more precise than manual dilution. Now I want to show you a technique where you can enlarge the calibration range even more than with dilution or with partial loop injection technique. Here it's called high-low calibration, and you have two calibration curves which you combine together. They have to be subsequently, and by logical decisions, the system decides if the blue calibration curve fits, for example, to sample A, or for sample B, the peak areas are this high, so here the calibration curve, the green one, is a better fit for it. So you have here a larger calibration range. For this high-low calibration, there are 3 different techniques which you can use. Of course, you could prepare all the standards manually, but that is really time-consuming. And here we speak now about 2 sets of standards, so maybe 10 standards. But you could also use MIPT, so the partial loop injection technique. Here you had to prepare 2 standards to calibrate the first or the high and the low calibration. It is used for microgram and milligram per liter range. On the other hand, you can also use the inline dilution technique. Then you have to prepare only 1 standard, and automatically from this stock solution, the high and the low calibration are done, and you use it for milligram and gram per liter range. And on top, you can compare the results of your samples if they are within the calibration range or not. If not, automatically a re-injection of the sample with an optimized dilution factor or an optimized injection volume is done. So at the end of your sample series, you have everything within the calibration range. This high-low technique is used if you have sample series with high concentration differences. And the advantage in comparison with inline dilution or injection loop, partial loop injection technique is that in the most of the cases you have to inject only one time your sample. And that means you save time. On the other hand, you have the advantage also that the results are always within the calibration range, so reliable results are guaranteed. You can use it for anion as well as for cation analysis in parallel systems, in independent systems, that's fine. Also, if you have only a very low sample amount, it's not an issue. Sample or systems are installed here with less than 1 milliliter sample volume for anion and cation analysis. The typical concentration range where you can use a high-low calibration is microgram per liter to gram per liter range. To show you a few results, here see a high-low calibration setup for an anion and cation analysis by inline dilution and inline ultrafiltration. In the middle part, one autosampler which handles the dilution and the ultrafiltration. On the right side, the anion system. On the left side, the cation system, both injection valves and series. The maximum dilution factor for such a system with inline ultrafiltration is 1 to 800. And by the calibration for low range is done here in microgram per liter range, for high in milligram per liter range. An application which is running for environmental samples, so here surface water, river water, wastewater samples. And I would like to show you also some results here from a system stability test. A QC standard was run 2 times per day within 14 days. And between the QC standards, a huge series of samples from the environmental field was running. Therefore, the concentrations you see for anions as well as for cations are different. So from 0.1 milligram per liter fluoride to 30 milligram per liter chloride. And you see the relative standard deviation for all these QC standards within 14 days. It's really excellent for anions as well as for cations. Now to show you some tips and tricks for calibration in ion chromatography itself. For example, I get quite often the question, how long can I use a calibration in ion chromatography? A recalibration is recommended after every change in the system. It can be a hardware change or a long-term stop or a new eluent. Of course, not every time after you use a new eluent you recalibrate your system. Here the recommendation is use check standards to verify your system. And with the check standards, be careful that the check standards are placed in the middle of the calibration range, not the first or the last calibration point. The recovery of the check standards must fulfill your lab requirements. For example, between 95 and 105% recovery, then it's fine, then it is not necessary to recalibrate the system. If it is outside of this range, automatically you can program your system in a way that automatically recalibration is done. You see here also in this table with green, you see automatically that everything is within the requirements. And have a look for tendencies, for example, by trend charts. Here we see an example, and at the first look it looks like a positive trend, but use also statistic functions. So if you set here warning limits, which are also depending on your requirements, it can be 2 sigma, 3 sigma, or a fixed amount, then you see, for example, this was not a trend. It was really excellent with less than 1% relative standard deviation here for this example. Another question of standards should be used in ion chromatography. Automatic calibration needs only one single multi-ion standard. This can be handmade, or you can buy it directly from a chemical supplier. If you prepare your stock solution by yourself, use the highest quality of the salt or the stock standards, at least PA as quality, and use ultra-pure water to prepare the standards to avoid contaminations. On the other hand, you can buy such stock standards. For example, Sigma Aldrich offers a platform where you can order customized standard solutions or use the Primus standard, that are premier multi-ion standard solutions for anions or cations. Be careful in ion chromatography with the pH and the solubility of the standards. That must be suitable for IC. For example, don't use AAS or ICP standard solutions. They are quite often in 1 molar HNO3, and that is too acidic for ion chromatography. Another point which I show you here is how long can a standard solution be used. The commercial standards which are available, they have expiry dates, so that's quite easy. And if you have opened the bottle, store it in the refrigerator. For handmade standards, milligram per liter standards, I would say you can use it for days. In the refrigerator, you can use it also for weeks. Microgram per liter standards, that I would prepare daily fresh. Also, I would remark that biological active substances or unstable substances, here you have to expect a shorter lifetime, and they should be stored always in the refrigerator and prepared fresh. Should I use peak area or peak height with calibration settings? Here, peak area is recommended in ion chromatography because you get a more robust signal. Peak height is only used in the range of the quantification limit, or if coelutions don't allow a robust identification of the peak start point and the peak end point, then peak height is used. Should I go through with my calibration settings? Not. That the point of origin should not be applied. Use only measured calibration points in ion chromatography. You see on the right side which uncertain here, or how wrong your results could be if you force the calibration curve through 0. On the right side, you see it is a better fit. Nevertheless, you have here an intercept on the axis. What is a good calibration? How many calibration points are recommended? If you use linear calibration curve, I would say minimum 3. For quadratic, minimum 5 calibration points are recommended. And they should be equally distributed in the calibration range. You see here an example for bromate with the triodide method, post-column reaction, UV vis detection, 0.5 to 5 microgram per liter. So an excellent calibration also here. And here the points are really equally distributed. And also, can say if it is a good calibration curve, look for the correlation coefficient. It should be higher than 3/9. Then it is really already a good calibration. The relative standard deviation is another parameter which you can check quite easily. Here you saw in this presentation quite often 0.5, 1%, but everything lower than 3%, it's absolutely acceptable. Higher than 5%, I would say there's something wrong and you should redo the calibration. And have a look for the axis intercept. It should be close to 0. If it is higher than that, that is an indicator that you have problems with blanks in the LON or in the standard solutions. So let me summarize. Automatic calibration, it is a technique that can save time and gain reliability. The technique can be used for anions and cation analysis in parallel in independent systems. Usually it is used between nanogram per liter and gram per liter range. So you see the complete concentration range. You can use automatic calibration, and the wide sample concentration range to analyze high and low concentrated sample in the same sample series is guaranteed, because all of these techniques has a minimum on cross-contamination. Even if you would like to enlarge the calibration range by high-low calibration, you have a technique where you can do it. So automatic calibration reduces the time-consuming, the error-prone, and the cost-intensive manual working steps, and you gain absolute confidence in your IC results. Thank you for listening.
Thank you, Andrea, for a great presentation. And some very practical tips and tricks. I apologize for the slight audio difficulties we experienced when the video slides were running. We will try and work on that. Thank you all for your questions. Keep them coming. We will get through as many as possible in the time that's left. The first question came in earlier today, and it's to Liz. If my lab can only afford one ion chromatograph, what would you recommend as the most versatile detector of the ones you've discussed?
Okay. Well, after talking about mass spec, I think really the cheaper option is to use something less specific. So probably a conductivity detector is the cheapest and easiest one to look at a whole range of analytes. But if you were specifically targeting carbohydrates, for example, then you might want to look at pulse ampermetric detection. But with respect to mass spec, generally I would say probably electrospirionization mass spec. But again, it depends on what you're targeting, really.
Okay, yeah. So it's very application specific, is what you're saying?
Yeah. So I think if you're targeting kind of one area, then you make that choice. But if you're kind of looking at a range of analytes, then you might want to go with something that can look for several different things.
Yeah, okay. The second question that I've got came in from Diane, and this is aimed at Andrea. My baseline is very noisy. What can I do?
Yeah, if the baseline of an ion chromatography system is noisy, it can have different reasons. First, I would check if I have no air bubbles in my LON, so if the inline degasser is working well, or if I have degassed my LON manual properly. If this is working well, then of course the noise could come from the pump, so maintenance of the pump could be necessary. But in general, all depends on the quality also of the chemicals, so ultra-pure water should be used, and the quality of the salts which are used for the LON preparation should be high enough that you have no contaminations by other impurities.
Okay. Okay. Another question that came in, which is from David, and this is for Liz. Oh, no, I'm sorry, it's for Andrea. Would the automatic calibration work with a hyphenated ion chromatographic MS system?
I think it would work. The ion chromatography part and such a combination is like a sample preparation part. We only separate the samples in the IC part, and how you enter the sample to this IC part, it doesn't matter. So it can be also this automatic calibration. No issue with that.
Okay. Another question from Pete, and that is, can you review the kinds of solvents other than water, methanol, and acetonitrile that are suitable for ICMS work, Liz?
Generally, I think you're fairly safe with kind of the HPLC solvents. There's been several work done using isopropanol or ethanol as well, but I think the real thing is to check your column and suppress compatibility is the main issue, and also the mass spec compatibility with it, because you don't want to destroy your column putting solvent in if it's not compatible.
Okay, good answer. This one is actually addressed to both of you, and it's from Paul. How do you distinguish between singly and doubly charged species in the same sample if they're present at different concentrations? Why don't you go first, Andrea?
In ion chromatography, you can separate the single and double charged species in the same run, and you identify the peaks using standard substances in a standard solution, for example. So you compare the retention times with the known standard substance with the peaks in your unknown samples, and by that you identify here if it is in, let's say, a chloride or a sulfate. So it doesn't matter if it's single or double charged, you identify via the retention time.
Okay. Anything to add to that, Liz?
That's generally how I would do it. I know that you can get charge detectors, and that can increase your signal for the doubly or triply charged species. But generally, most of the time they're separated. So it depends on the concentration, really.
Great. And then I've got one from Laura. Can you comment, Liz, on practical suggestions for improving the signal-to-noise ratio?
Well, I guess kind of going on from the noisy baseline, the first thing is probably kind of check your instrumentation. So if your pump or your suppressor aren't kind of working efficiently, then that can increase your noise. And also, if you've got an older eluent, then that can sometimes lead to baseline drift. That will affect your noise. Another thing you can do is you can increase your injector loop, and that will inject more analyte onto the column, which can increase your mass sensitivity. But it can lead to band broadening. So it's kind of a bit of give and take.
Okay. We did have one general question, which was sent in by James, saying, could he get a copy of the presentations in PDF form? We have discussed that as a team, and yes, we can make those available. Anybody that's interested, if they could send an email request in to rob@intlabmate.com, and he will satisfy that requirement. Another question, this one's for Andrea. How difficult is it to flip a system between anion and cation modes, or do you suggest having two dedicated systems?
To change between anion analysis and cation analysis,
yes.
It's not a big issue, so you can do it with one system. It takes you about, let's say, 1 hour. First you have to stop, of course, your anion analysis. You remove your anion column and the suppressor, and then you rinse your system with water, ultrapure water, and then with the cation eluent, and then you install your cation column and wait until the system is conditioned. So usually 1 hour for that. So 2 dedicated systems, it's only recommended if we speak about trace analysis, ultra-trace analysis, where it takes time to rinse out all contaminations from one to the next type of analysis.
Okay. And I guess that if they had a very high volume of anion and cation analyses to do in a day, then it would make sense to have 2 systems.
Correct. So it's always a question of capacity. So if you have a higher sample throughput, then two systems maybe is a better choice. In general, it would work with one system, but depending on the sample capacity which you have.
Okay. I've got another question here. There were actually two questions on the same subject, which was partially covered in your presentation, Andrea. What happens if an analyte in my analysis is vastly overconcentrated and outside the calibration curve? And then there's a little bit of a follow-on to that, saying if they had multi-species in there, multi-ion species,